bet you we could make some rap about Lsrl. Maybe that's a good band name. But realistically, we're going to talk about it in the stats realm. What is Lsrl? It is actually a least squares regression line. We're going to talk about what that is in a second. This is section 3-2A. We got two goals for today. Number one, to be able to define all the values and variables in a least squares regression line. And number two, to be able to write the equation of least squares regression lines depending on what you're given. All right, so what is a regression line? A line of regression is a line that kind of shows, and you might have heard the term regressing towards the mean. It is a line that describes how a response variable, which is y, changes as an explanatory variable x changes. Okay, so you can see off to the right, we're going to actually use this example. There's a whole bunch of data there, and it's in a scatter plot, and there's a line through it. That is called a regression line. It's kind of showing the trend of the data, so it's oftentimes referred to as a trend line. Sometimes it's referred to as a line of fit, or line of best fit. We're going to most often call it a regression line or a least squares regression line. So what is this line? What do we know about this line? So a regression line relating y to x has an equation in this form. It's very similar to y equals mx plus b, except we have a plus bx. So we're putting the y-intercept in front and the slope part in back, and we're also using this little thing on top. It's called y hat, and it's referring to predicting things. Okay, it's the prediction. If it was just y, it would be an actual value. These are predicted values. So what is each part? And you need to know each of these parts so that we can actually describe this data, describe the parts of this regression line. So the y-hat is the predicted. It's the predicted value of the response variable. Okay, x is just the explanatory variable. So we've got y-hat, we've got x. The b value will have a number. It's the slope. But in context, it's the amount by which the y is predicted to change when x increases by 1, or 1 of whatever it is. And that's the b. It's different than in slope-intercept form where we have the b as the y-intercept. This is the slope. And then the a value is the y-intercept. It is considered the predicted value when x is 0. So think about a y-intercept. It's wherever the x is 0. You take that y value, and that's the y-intercept. It's on the y-axis. That's what this is. But it's a predicted y value. So let's look at an example of this. What can you do with a set of data? If you have a random sample of 16 used Ford F-150 Super Crew 4x4s that were selected from Autotrader.com, and here's the data. And it's just comparing miles driven to the price. Okay? If I want to see this as a scatter plot, I can simply go to my calculator, and maybe not simply because there's a lot of values, but I can go to Stat, go to Edit, and put all these values in there. I already did this ahead of time. And then I can graph it. So reminder for graph, you have to go to second y equals, which is Stat Plot. Turn on one of them. Make sure it's on Scatter Plot. Make sure list 1 and list 2 are in there. And then you can go to graph. And if it doesn't show up good, you want to do zoom 9. Zoom 9 is your stat one. It should show that stat plot. And there's my scatter plot. Okay? Now you can kind of copy that down. If it's a little bit easier, though, to put numbers to it and not look at that, then you don't have to. But that graph, that scatter plot, will look something like this. Okay? Which is pretty much what I just saw on my calculator. Now, what if I want to see the actual equation of the line? The calculator will do that too. All right? You can utilize what you put in there. I'm going to go second quick, get out of there. I'm going to go to Stat. I'm going to go over to Calc, and I'm going to go down to 8. Linear regression, where we're using a plus bx. This is the common statistical format. So we're going to use that and click on that. I've got list 1 and list 2. I'm going to go to calculate, and guess what? Boom. Now on this, it will give me the a value. It will give me the b value. It'll also give me the r squared, which we haven't really used yet, but the r value, which is our correlation, is on there as well. So you have your a and your b. All you have to do is put it into the equation. And it'll look something like this. Y hat equals 38,257 minus 0.1629x. And I do want to just point out that sometimes some people write it as, like with more context, the y hat is the predicted price. So they would say price hat equals 38,257 minus 0.1629. And instead of x, they'll say miles. So just know that that is actually common. You might see that written like that. No x and y, no variables, just the words for what they actually are. But here's what I want to talk about. How can we define all those variables and the numeric values in that equation? This is also a very common question. When it comes to AP exams, I've seen this one a lot. So we want to be able to identify the variables. So that's x, and that's y hat. And then we want to also be able to identify the values, which is 38,257 and negative 0.1629. We want to actually give words to what those mean. So what is x? X is the explanatory variable. It is the number of miles driven for a truck like this. I'm not going to write out the used Ford F-150 4x4 Super Crew. I'm not going to put all that down, but it's a truck like this, okay? The y hat is the predicted, and we said this before when I showed what they are. We need to say predicted. It is not an exact price because we're looking for predicting things. So it's the predicted price of a used F-150, we'll say, like this. Okay, so that's what we're looking at. Now, what do those numbers represent? What are the numeric values? The 38,256, yeah, that's the y-intercept if you look at it that way. But what does that mean? It is, again, the predicted, because it's not exact, it is a predicted price of a truck that has 0 miles. So it's a brand new truck. We're saying that's the predicted price based on our model. And then finally, negative 0.1629, that is the predicted, that's the slope. That's the predicted decrease. It's always a change in price for each added mile. So every time you add a mile, it's essentially bringing down the price 16 cents-ish. So that's how you can define all variables and numeric values. It's a common question. So I'm going to come back to one of those in a little bit. Now, where do we get that line from? So in most cases, no line will pass exactly through all the points in a scatter plot. That's because the lines have to be a perfect 1 correlation or negative 1 correlation. So a good regression line makes the vertical distances of the points from the line as small as possible. So I can make a line that I think, okay, I'm going to kind of go through here. I think that's going to be pretty close. But these vertical distances, whether it's up or down, like the bottom of the line, we want to have the smallest vertical distances. And if it's a true least squares regression line, it will do that, and all these distances, these are called residuals. We'll talk about those more next time. All those residuals would add up to 0. If you have about the same amount on top and bottom, it should add up to 0. But there is that line that actually can be done perfectly, and it's called a least squares regression line. So that's what my next vocab term is. Different regression lines do progress different residuals, but the regression line we want is the one that minimizes the sum of their squared residuals. So you're taking those, squaring them, because some will be negative, some will be positive, and that'll make them all positive. Add them all up, you want the smallest the smallest sum of those. That is called the least squares regression line. And that's what we're going to be working with. That's what you're given in your calculator when I showed you before how to do that. That's what we're going to be working with is the least squares regression line, Lsrl. So let's go back to that least squares regression line. So there's some things we can do with it. The main thing is we want to be able to predict things. So it is considered like a trend line that shows trend, and we can use it as a predictor. Which sometimes is great and sometimes not so great. So here's the line, here's the equation, and here's an example. It says predict the price for 100,000 miles driven. Because if you look in here, there's nothing around 100,000 miles from the data we were given. So let's predict. Let's take this least squares regression line equation and plug in. Let's plug in for x because that is the number of miles driven, and we're going to plug in 100,000. And what do you get? Well, you get a value that, seems realistic to me. It is 21,967. That is $20,967. That is our predicted price at a truck that has 100,000 miles. Follow-up question. What about a predicted price for 300,000 miles? Because trucks tend to last a while. And so what if we want to change it to 300,000 miles? I'm just going to change this 1 to a 3. What do you think you'd be paying for a truck that's 300,000 miles if you really wanted to buy one that much? Well, if you plug it in, you get negative $10,613. Which essentially means someone's going to pay you $10,000 to take that truck? I don't think so. And that's where it's not so realistic. And we can't always use this predictor line or this least square regression line. It's called extrapolation. So we can use a regression line to predict the response for a specific value of the explanatory variable. The accuracy depends on how much data scatter is around the line. While we can substitute any value for the x and figure out a prediction for the y, we must exercise caution in making predictions outside of the observed value. So that is called extrapolation. It's the use of a regression line for the prediction far outside of an interval of values of the explanatory variable x used to obtain a line. So such predictions are often not accurate. So we can't use them. We don't want to do that. That last example was a good example of why. All right? Now, I'd like to draw your attention to a separate way to find the equation of the line that you might not be able to use your calculator so much for. So if you go to your formula sheet that's given for the AP exam, we've already talked about this. This is finding mean. We've already talked about this. This is finding standard deviation. We've actually already talked about this too. That's R. And now we've talked about this, which is our general equation for a least square regression line. So what are these two things? Well, sometimes you might be given summary statistics instead of an actual set of data, and we need a way to find the equation of that line. And this is what we're going to use. Very similar, we can use means. So the equation y bar equals a plus bx bar. This is usable to find missing parts. Now, you might think back to algebra and you might know a slope, you might know a point, and you want to find the y-intercept. We're going to do kind of a similar thing, but we need to at least find the slope first. And this is how we can do it. Find the slope first. And the formula for finding slope is the correlation, the R value, times the standard deviation of y over the standard deviation of x. So keep those handy, because we're going to look at an example right here. It says a scatter plot of the number of attempted shots a basketball player takes and the number of points they make seems to indicate that there's a linear relationship. Information based on a random sample of 8 basketball players yields a correlation coefficient of 0.84. Pause right there. What is a correlation coefficient? Well, that is our R value. That's the correlation, 0.84. With the following summary statistics, Use this information to generate the equation of the least squares regression line and to define all variables and numerical values. So there's a big and there. So we need the equation and we need to define all of them. Let's find the equation first though. So what we're given is the average number of attempts was 18. That is our x bar. And the standard deviation that goes along with that is s sub x, that is 3. Our average number of points, our y bar, is 20, and our standard deviation that goes along with that is 4. So if I want to write the equation of this line, I'm going to first figure out what the slope is. We need both the slope and the y-intercept. So I would start, number 1, find the slope. That is b, and we have a formula for that. It is b equals r times s sub y over s sub x. We just saw that one. So if I go to this example and I plug in, I know my r is 0.84. I know my s sub y is 4 and my s sub x is 3. If I plug those in and get a value for b, it is actually 1.12. And I've got my b value. Now that I've got my b value, the other thing you need is your a value. That is your y-intercept. So that's going to be my step 2. Find a, or our y-intercept. Okay, remember, we know y bar equals a plus b times x bar. And we have 3 of those pieces now. So let's plug in and find the missing one. So I'm going to take y bar, which we said was 20. We don't know the a yet. The b is, we got 1.12, and the x bar is 18. That's given in our problem. I solve that, and I get a equals negative 0.16. I now have my a value. And I can write the equation, which is going to be step 3. Write equation y hat equals a plus bx. So my equation will be y hat equals negative 0.16 plus 1.12 times x. There's my answer. So it takes a little bit of algebra to find the equation if you're given those summary statistics, but it's not hard algebra. It's just some plugging in and using a formula. But part 2 was define all variables and numeric values. I'm going to do that real quickly here because we talked about this before. So x is number of attempts, shot attempts. Y hat is the predicted number of points scored, depending on the number of attempts. We've got that negative 0.16. That is our y-intercept. So that is the predicted number of points for 0 shot attempts. Oops, shot. Which doesn't make a whole lot of sense. You're not going to get any points, and you're going to have negative points if you don't shoot. But for the sake of the problem, we're using that follows the trend. And then lastly, 1.12. That is the predicted number of points for each added shot. So you shoot again, you're going to get about 1.12 points. That's how I can summarize and interpret all those values. So if you'd like to pause it here, I have a second example you can try on your own, and you can unpause it and check to see how you did. Basically, it's talking about advertising, comparing like putting money into advertising and then what you get out of it for number of items that you would sell. Gives you a correlation coefficient of 0.74 and the summary statistics there. right, so here's all what I got. I'm not going to show you all the work for getting the equation, but it is y hat equals 44.36 plus 4.44x. And then I have all the different parts listed here. X is the cost of advertising in thousands, so maybe add that in there. Thousands of dollars. Y is the predicted number of items sold. It's predicted, and it's also in the thousands. That 44.36 is the predicted number of items sold at $0 of advertising. Items sold in thousands again. And 4.44 is the predicted increase in items sold for every $1,000 of advertising added. So you can see that there is some benefit to doing that marketing, that advertising. All right, last thing, real quickly. Last way you might be asked to find the equation of a line is from a Minitab or computer output. Okay? So these computer printouts are going to look very similar to what's here. And there's going to be some things in here. For right now, we need to know this. We need to know this. And we need to know this. Those are the main things that we're going to be using here. I do want to also highlight this right here because this does give you a piece of information about the problem. So basically, if you're given this computer printout, which is kind of common in stats, there's different computer programs that are used for statistical analysis, and this might be given. It will give you a constant. A constant is going to be whatever your y-intercept is. So the constant is the number that's just there. So that's going to be your a value. So wherever's next to that is your a value. The coefficient for the x variable, well, the x variable will be listed, whatever it is. That's going to be your explanatory variable. And what number goes with the x variable? That is the slope. That is the b. I'll leave it this color. That is your slope. So the slope is given. So from that, then you can easily write your equation. Y hat equals a plus bx. And that's all you need to find the equation. But one other thing that's in here is r squared. It's called the coefficient of determination. I'm going to write it out here. Which we'll talk more about at a later time. But that r squared value, if you want to find the r, the correlation, it is by taking the square root of r squared as a decimal. And then technically you should do plus or minus depending on the slope there. So see the slope for that. But you can also find that, not necessarily today, but that's another piece of information. Everything else we're going to use at a later time or not use at all. So my example here is here's a computer printout. It's talking about from the Minnesota Department of Transportation. They're looking at their new weight in motion scale because to weigh vehicles on a highway. Or actually, no, to see if a new device was weighed several trucks when they stopped. So they're trying to figure out stopping and how it relates to weight. So I would say this is my x. It's the weight in motion. But then from my equation I have my constant, which is my y-intercept, my slope, which is my b, and I can already write y hat equals 10.854 plus 0.63791 x. There's my equation. And from the situation, then I could also explain all the different parts of it. But I have the information there. We just got to identify which is which. So that's the third and last way that we're going to talk. I wanted to talk about finding the least square regression line. But that is our goal. Our goal is to be able to write the equation of a least squares regression line and also define the values and variables in it. So that's section 3.2a. We'll see you next time.